Всем добрый день. Очень рад всех приветствовать. У нас сегодня, на удивление, первый в истории нашего семинара удаленный доклад. Как-то мы до сих пор справлялись всех приглашать лично. Но вот на этот раз у нас доклад из-за рубежа. Естественно, лично приехать было бы странно. Яны Вейцман, The Expressive Capacity of State-Based Models, a Formal Language Perspective. Яна, прошу.
Yes, I think I will switch to English here, as this work has primarily been done also with my English-speaking colleagues, and I'm not sure I possess all the terminology to give this talk in Russian. So hi everyone, my name is Jana. I'm currently a first-year PhD student at the University of Göttingen in Germany. With this work on expressive capacity of state-space models, we have done last year with my colleagues Yash Saraf, who is currently a PhD student at Saarland University, and Professor Dr. Michael Han, who also works at Saarland. And this work is has been admitted last year to Europe as a poster. So I would like to preface this talk with maybe two things. One of them is that I think this talk would be a combination of a theoretical and an empirical. I will try to give high-level intuitions for some of the theorems that we have in the paper, but also I would try to cite some of our empirical results. And the second, I guess, comment or remark that I'd like to make before is that I have been away from this work for a year, and I'm not really keeping let's say, track of what is happening with SSMs now, because I don't really work with them anymore. So I hope not much of this is already somehow outdated, or with some new state space models that might have come out in the past year. With this, I hope that we will fit this in about an hour of the talk itself, and then we can dive deeper with questions afterwards. So let's start. Initially, we all know that transformers are a great architecture, but sometimes they're not good at all tasks. Sometimes they really failing. And even though they're widely used right now in most of LLMs, and they are a backbone of the majority of LLMs nowadays, there are also different architectures. Well, some of them could be called, impractical and outdated, but on some tasks, they used to perform better than transformers. But in the recent years, modern SSMs appeared, which were very shiny and very promising in 2024 when Mamba first came out, which is at the central point in this paper for most of the empirical results. SSMs appear to be very, very, very promising. But as we figured out, they still desperately fail at some tasks that are easy for transformers. So overall, all architectures have their advantages and disadvantages, and are better at certain tasks, but are failing at others. So the question that we were interested in kind of primarily when we started working on this topic was, well, how can we determine that one architecture is better than the others? Ideally, we cannot really say that some architectures are better, but they can be more suitable for different tasks. And this is where theory is coming in, and where it's going to play an important role in basically understanding what can potentially be done and what cannot. And since this paper deals with expressivity, I think it would be wise to introduce what expressivity is in general, and what we are kind of limiting ourselves to here. So we can imagine all the possible set of tasks that our architectures can be dealing with. And some of these tasks can be expressed in a certain architecture. So we can construct we can have a certain construction that would express this task, which does not necessarily mean that this task would be possible to do in practice. So expressivity does not inherently imply learnability. And there are some empirical gaps where a construction might exist, but the experiments would show that, for example, length generalization is not possible, or a certain task is not learnable, even though expressible. So in this work, we are primarily dealing with this blue circle over here. We are dealing with the expressivity of state space models, but we do not necessarily claim that all what we find to be expressible can be learnable in practice. Sometimes it can be, sometimes it cannot. And in general, expressivity as a subfield deals with this whole problem of, well, how do we find the exact border of this blue circle, and how do we understand why there are certain gaps? So this was also something that Michael Hahn's lab is interested in doing in Xyland. And now a bit more than topical about SSMs. So as I noted before, SSMs, when they firstly, the modern variant of SSMs, when they firstly appeared, something like Mamba, they sounded very promising, potentially because they were tackling this two disadvantages of comparatively RNNs and transformers, where RNNs had linear inference but were not parallelizable in training, and transformers at inference time had this quadratic complexity, but the training was parallelizable. So SSM's modern variants introduced this these two properties being a bit more desirable, in the sense that training was parallelizable and inference is linear. While different SSM papers, different state space models that came out in the recent years have different primary equations that they use, we are kind of keeping ourselves to this one here. So we have this element-wise product of the hidden state that gets updated with the A gate, which controls how much of the input we are going to keep. And we have this residual kind of connection that's done with this B matrix, which kind of introduces a new information. This allows us for the recurrent design, but kind of avoids the nonlinearity that was more common in RNNs. So this is how the hidden state is updated. This allows us for faster training. And also, if we take A as a common factor, we can view it as also as a convolution. So you have this kind of a double lens to look at the SSM, where you can look at it as both a recurrence and a convolution. And the more modern version of it would be something like a prefix scan. So the convolution view would be, I would say, more appropriate in the context of time invariant SSMs. So, as I've previously said, there has been quite a lot of research on expressivity of RNNs and transformers. However, by the time we have started doing this research on SSMs, there has not been as much on the expressivity of them. One of the first papers that has appeared actually that year in ICML was a paper by Will Merrill that was pretty much the only paper that has ever dealt with the expressivity of SSMs until that time. So for us, it was a clear gap that we kind of wanted to address with this paper. But I think the first point when we arrive at SSM is that there are many different models, and yeah, here they call linear RNNs, but this is just because there is no nonlinearity, so this is pretty much equivalent naming. There has been so many different ways people have defined different models. Like in the bottom left, we have Mamba, but also there have been Griffin, RedNet, Megalodon, GLA, and so many different variations. So we kind of wanted to have a more unified perspective on all those different definitions in a similar way that we have kind of a unified way how we approach defining attention in transformers. So that's why we, in our paper, use the following equation for a single layer SSM. So we define this, this as a map at the arbitrary length C. And this is the equation with which we are updating our hidden state. And then for basically the norm is just a linear norm. And we are, with this mixed operations, we are absorbing the linear unions, GLU, Swift glue, and Swiss glue, and so on. So this lets us talk about SSMs in a more unified way, let's say. And I guess also two important distinctions that we are making here are for the two types of SSMs. The first one, the SSMs can be either time invariant or non-negative. In the time invariant case, our matrix A, our gate A, is not dependent on the XT. So some of the examples of those models are Hungry Hippos or RedNet, and some of the examples of these are the examples of time invariant. The other way SSMs can be designed, so another design choice that one can undertake is forcing all the entries in the A matrix to be non-negative, which is a classic example from this work is the Mamba. And funnily enough, when we started working on this that year, both RedNet and Mamba were rejected from ICLR, even though they have been great architectures, great papers with great background. I think when we were working on this, it was pretty funny to us that such cool things were rejected from one of the top conference. In any case, so the way we approach expressivity is in context of state-space models, and how also people often approach it when they study expressivity in RNNs and transformers, is by using the framework of formal languages. So by defining whether a certain formal language can or cannot be expressed, we can talk about certain properties of architectures in terms of expressivity. And firstly, one of the groups that we consider is the star-free languages, which is just a regular language class that is closed under finite union, product, and complement, but not so under Kleene star operator. So, for example, this AB star can also be rewritten without using this operator as a complement of having a string starting with a B, having a string ending in A, having two A's or two B's in the middle, and then we just take a complement of that. So these definitions are, in that sense, equivalent. We'll also consider non-star-free languages, which is basically all regular languages that are not star-free. So the only difference is that these languages would require a Kleene star operator for their definition. And this is one of the examples. So this one could not be rewritten in the same way as the previous one. One of the very simple examples of a non-star-free language would be something like parity, and parity has also been widely studied in the context of transformers and RNNs. So parity function is simply something like determining whether a number of ones in a bit string is even or odd. So this is a pretty simple case, and we could also define it just as a star with an additional neutral symbol. So we are basically looking for this pairings of the symbols in defined alphabet. What we distinguish between for working with formal languages in this context is recognition and predictive modeling. So in the case of recognition, this is basically we're trying to say whether a certain string belongs in a certain language or not. But in the case of predictive modeling, our task is a little bit more difficult, but it's easier to look at it in that way in context of training models. And in the case of predictive modeling, what we are doing is basically we are looking further to understand whether the next, we're looking to output the next valid symbol for that language. So if we were doing parity in the first case, that would be just 0 and 1. And then in the second case, we can either consider continue the sequence or output the end of sequence character, which basically outputting that character is equivalent to saying that this string belongs in that language. So this basically allows us to kind of talk about both concepts and a bit more naturally in the context of language modeling as well. And now back to parity. So parity, it has been proven that RNNs can recognize parity very well because it can be represented with this simple finite state automata. So for RNNs, that has been pretty easy. For transformers, the situation is a little bit different. So this has also been done, has been shown by the work of Michael in ACL 2024. So parity can be shown to be a sensitive function. So the function where every single input bit can flip the output. And transformers have been shown to be biased towards learning low sensitive functions. And since parity is a high sensitivity function, the loss landscape of transformers on parity is very brittle. So learning parity is very difficult for transformers in comparison to something like majority language, for example, which has a lower sensitivity. So RNN is doing good on parity, transformers not so well. But how do state space models perform? Well, if we rewrite our basis equation in a more, let's say, graphical form in this way, and we remember the FSA that we use for solving parity, we can think of it that way. We set our B to 0 and we only use the A gate to represent parity. And well, A could be, the result of this operation could be either -1 or 1. And this is how we kind of perform this construction. So there is this a trivial one-dimensional recurrence that computes parity. Then the sign of the hidden state encodes the parity. But the problem with this is that this would require a negative gate. And since modern SSMs are either time invariant or non-negative, this introduces a problem. So here is how we kind of arrived to this conclusion. Since we would want ideally to have this A to be either -1 or 1, we cannot have it in a non-negative variant of an SSM, so for something like Mamba. Hence, we would not be able to learn parity. So the first theorem that we introduce in this paper is that non-negative SSMs cannot recognize parity at arbitrary input length and the finite precision. The more formal argument focuses on the kind of an extreme case, on the inputs of the form 1n, so kind of more generally simple periodic inputs. And in this case, our activations, as n grows infinitely large, will converge. However, this is not something that we want because the parity itself keeps oscillating. So the output is changing as we are introducing more and more input. But since we are having this convergence, we have the fact that, well, we arrive to the fact that, well, our B metrics, basically B and A, become constant. And we either would diverge exponentially with alpha greater than 1, converge with alpha less than 1, or just diverge linearly at alpha 1. And this would not really change if we take care of the norm or the mixes. However, there is, we've been talking about non-negative SSMs. There has to be a slight remark to be made in case of time invariant SSMs. So we also show that they also cannot recognize parity, even if we allow complex valued gates, as long as each entry in that matrix A has a rational angle in the complex plane. This would also not be possible. So we have not really looked in this work in a more proper construction for something like irrational angles, so that would not be as possible also with the finite precision. So in this constraints that we impose, so the finite precision and arbitrary input lengths, even with complex gates in time invariant SSMs, we would not be able to do it. So in no case any SSM would be able to represent parity. So our first takeaway that we arrive here is something like, well, SSMs will struggle with modular counting, and parity requires modular counting of 2. And non-star-free languages in general require it as well. And these are some empirical results. So some experiments that we ran on some non-star-free languages. The transformer results here are taken from the Bhattacharya et al. Results from EMNOP 2020. So the orange bars, the orange solid bars, are in distribution results for transformers, and the results with these little bubbles are the out of distribution results for transformers that have been taken from previous work. Our results for Mamba are the blue ones. So blue solid is in distribution, and blue with this bubbles is out of distribution. So empirically, we are also able to see that SSMs will not really do well on non-star-free languages. And in general, any language that would require modular counting would be difficult to do. And as we've seen, for both time invariant and non-negative SSMs, that would be the case. Another languages that we consider is that is the family of flip-flop formal languages, which has been introduced by Bingbing Liu's paper in NeurIPS 2023. Here we have 3 sets of instructions. W stands for write, I stands for ignore, R stands for read, and we have 2 possible bits, 0 and 1. And the primary feature of this language is that if you have a W then followed by a bit, then the next time you see a read instruction, you're supposed to output the last written bit. So in this case, only 0 is valid. And this family of languages has been previously introduced as kind of this minimalistic long-range dependency benchmark, because you can have a very large distance between when you have written the very last bit and when you have to output it. And it has been loosely argued to be a proxy for closed domain hallucinations, because, well, the answer is in the context that you are giving the model. However, in transformers, it has been shown that transformers are struggling with this language. While LSTMs are doing pretty well, so we can converge to a solution very pretty fast. As I noted, in this work, they show that this is not the case for transformers. So no matter how big your hidden dimension is, how many attention heads you have, or how many layers you're using, this is not really going to be the case, and this is pretty hard for transformers, mostly because attending to this last written talking requires a very strong positional dependence and attention score, which is not really something that transformers can do well with the most modern positional embeddings, because they are kind of this order agnostic in a sense, and having to attend to a single token is a bit more difficult. So hence, transformers and LSTMs in the past have been shown to have this disparity. We have also kind of extended that result. So this has been shown with the kind of toy transformers of very few layers, very few hidden dimensions, and we extended this result to pre-trained LLMs. So this also holds in practice, but this is a little bit of let's say, a spoiler, and also maybe not as relevant in the context of this work, but this is just to say that this theoretical results also scale empirically. Well, and the flip-flop in general can also be viewed as a set-reset automation, where we have this FSA, where the state also belongs to the alphabet. And so when we get the new input, if our input is a state, we simply transfer to that state. And if we get a bit, then, well, in that case, we just keep track of that bit and we store it. So this helps in keeping recording the last symbol bit from the designed set queue. And how we arrive at the construction for flip-flop like languages, well, here we have this 2-layer construction, actually. And what is happening in the first layer, and this is also done for finite precision and unbounded input length. At the very high level, layer 1 encodes local information. So we local information such as current symbol and the previous symbol in a way that is stable under normalization. So if we encounter the instruction symbol, we store it, and then if we encounter the bit, we set our B to 0, and we also are able to keep our stored bit in mind in that way. So at any point, we have the access to the latest instruction as well as the current token, even if after applying mix and NOR. In the second layer, we are actually implementing this set reset logic. So if the previous symbol indicates a write, then the current bit is stored and in a dedicated component of the state. Otherwise, the state is carried further. So in this case, we are able to use this construction to show that flip-flop-like languages, and in general, the languages that can use the set-reset automata can be expressed by SSMs. Does this hold empirically? Well, yes. Empirically, we tested this on Mamba and Griffin, and actually, this can also be done. So by itself, this also is pretty much already set-reset automata. So in some sense, even in one layer, this should be possible. And the green line is in distribution result, and the orange line is out of distribution result. So in that sense, yes, SSMs are different from transformers, and they resolve this critical failure mode of self-attention in being able to keep track of this last written bit, but we'll come back to it a bit later. And just to recap, we have this two-layer SSM construction that can predictively model the flip-flop language with finite precision with arbitrary input length. But does that mean that, well, SSMs are kind of just better than transformers? Well, not really. We wouldn't draw that conclusion simply because there are still things where transformers are better. And one of the examples is the copying task. So this ICML paper from 2024, they've been empirically testing some transformers, some SSMs, and they've showed that transformers on copying in general do much better at larger length than at a smaller length. So in this sense, the abilities of transformers and SSMs are in some sense complementary. Some things SSMs are doing better, some things are better done by transformers. And one of the takeaways that we are kind of trying to hint at here is that, well, maybe the future of architectures is actually hybrid. Maybe we could combine the best abilities of SSMs and transformers and have something that would work for both cases. And some research has already been done in that direction. I think this figure is actually taken from this paper by Walefe et al., an empirical study of Mamba-based language models, where they show that, well, actually, hybrid architecture is doing better than transformers or Mamba alone, which is kind of nice, but it's still unclear in terms of it's harder to do and understand expressivity of hybrid architectures from the theoretical standpoint, and it's also not very clear from the empirical standpoint of how you combine layers, how many layers do you need, and so on and so forth. So the architectural choices are a bit more subtle and less intuitive in the sense of hybrid architectures, even though from the first glance, it seems that they are doing better. We're going to go back here to the star-free languages that we have previously introduced, and we are going to use pretty old results. In the paper, we use pretty old results, well, relatively old, I would say, from Krohn-Rhodes, so Krohn-Rhodes theorem and Schutzenberger theorem, which basically allow us to introduce it allows us to say that all star-free languages can be reduced to this flip-flop state tracking. So any counter-free finite state automata can be rewritten as a cascade of simpler set-reset automatas. So In the paper, the proof is a little bit more elaborate, so I wouldn't go in detail here. But in general, in the paper, we show that using Cronrode's theorem, this cascade of simple automata can be equivalent to stacking SSMs, which allow us to say that non-negative SSMs can predictively model regular languages if those languages are star-free and we are still operating with the finite precision. Empirically, this also holds. So in case of transformers, you can also see the comparison with transformers here, but we can see that star-free languages can be expressed and learned by state space models. So both in distribution results and out of distribution results for Mamba converge. In the past, it has been shown, well, that by this paper, which introduced BRASP language, it has been shown that the exact categorization of transformers in finite state case is difficult. Hence, like not all star-free languages here work well. But with SSMs, it is possible. So in that case, that's also some advantage that SSMs have over transformers. Another thing that we're kind of slightly moving towards, let's say something that's more applicable for natural language is unbounded counting. The star-free results covers the regular languages, but state space models have continuous hidden states, so they can also simulate certain context-free and beyond regular patterns, especially those that require unbounded counting, but not modular operations. So it has been also shown that LSTMs can do this pretty well, and transformers also do unbounded counting in a way. So if here it's maybe not the most intuitive plot here, but in general, if we think of this unbounded counting in the form of, okay, we have to keep track of opening and closing brackets, this can be done by LSTMs, and also transformers also have some sort of mechanism where they can do this unbounded counting. So for example, here we have an opening circular bracket, we're operating parentheses, and we have an attention score of -24 at that token. And then at the closing parentheses, we have kind of the same token with a positive value, which is not always the case for all of the parentheses, but in general, it can be empirically also seen that transformers emulate this counting like behavior. For the SSMs, we think of the, let's say, language AN, BN. And here the important note, well, kind of a reminder that we have in mind is that, well, we do not allow for non-negative SSMs for A to be negative, but we can allow B to be negative or positive. So in that case, our construction for AN, BN for unbounded counting case becomes pretty difficult. So basically you are just counting up, and then once you start with the other symbol, you just start counting down, and this is fairly simple. However, this is where the gap between learnability and expressivity comes in, because we were not really able to get this results in practice. So even though the construction is fairly simple, and it also seems logical that we should be able to learn this, In practice, SSMs are lagging behind and are not really generalizing. So if we are looking at those bars that are non-solid for the bin 51 to 100, we can see that Mamba does not have a generalizable, did not learn a generalizable solution for those. So some further work would be nice in this direction to kind of understand why this gap exists, but this is to add to the previous statement that, well, not always what is expressible is learnable in practice, and we don't really know why. So this result brings us to the fact that, well, SSMs can predictively model languages like Dyke, Shuffle Dyke, ternary Boolean expressions, and languages of the form ANBN, ANBNCN, and so on. One, however, kind of relaxation that we have to make here is on the finite precision side. So here we modified this finite precision assumption by saying that since we have to count in unbounded manner, we have to allow for an unbounded number of integer bits. However, we still keep the finite number for fractional bits. So this is the only modification that we have to make in this case. Another interesting case, this is actually more related to also natural language, and people have loosely connected it to natural language in the past, is the case of bounded Dyke, for example, Dyke KM. So K stands for the number of different types of parentheses that we allow, and M stands for the depth. So in this case, we are using a stack normally to keep track of how many parentheses we opened and closed. And very loosely, that can be connected to how in natural language we have this nested sort of sub-sentences. So here in the example, they see that laws the lawmaker makes, and they report their question. So this can be seen as this bounded hierarchical structures, which are loosely related to this formal language. And interestingly enough, this has also been extended empirically with this work by Huetad, this year's ACL, where they show, where they actually connect bounded Dyke languages to natural language, and they show that if you pre-train on bounded Dyke, you can achieve the same performance, the same final performance of the model after pre-training with fewer tokens. So pre-train on formal language, then pre-train on a natural language, and your evaluation performance will be the same at the fewer number of natural language tokens, which is a pretty nice empirical result, especially for low resource languages. But I guess this is more also of a digression, just to illustrate that this theoretical result is important in the empirical context. Well, firstly, what about how transformers and LSTMs do on bounded Dyke? So LSTMs can express bounded Dyke. Transformers would require specific positional encodings, so it's not really stable for all of them. And then the dimension of the hidden state required to express bounded Dyke is a bit different for LSTMs. That's M log K, and for transformers that's just log K. But then again, this caveat of positional encodings comes into place, and this might be good references for anyone who would like to dive deeper into how LSTMs and transformers do it. But what about SSMs? Well, Dyke KM is a regular language, so the solution is guaranteed, but we were kind of not sure initially whether we can achieve an efficient solution though it was nice to discover that explicit stack is actually not required, and we can have this shortcut through counting. So the construction that we introduce for bounded DAG is hence efficient. So in the first layer, we kind of implement this clipped depth counter up using our previous unbounded counting results, but with clipping at M. And each timestamp, we know the current depth. And then in the second layer, for each depth level, we simulate the set reset automation that remembers the type of the open bracket at that depth. And then in this case, each automation needs just O log K dimensions to encode the K type of brackets. Does this hold empirically? Well, yes, and this is actually very clear here. So if you remember our flip-flop results, we were able to converge even at only one layer, though our construction required 2 layers. Here, we have 2 layers, and there's a very nice distinction in the learnability part between the 1 layer and 2 layer, where the 1 layer is the green one and the 2 layer is the orange one. So for 2 layer, for 2 different SSMs, for Mamba and for Griffin, we are able to converge to a solution. So as a small recap, a 2-layer SSM predictively models bounded DAG with the hidden dimension of M log K and with the finite precision as well. Which is very good news for natural language as well. So in that sense, SSMs appear to be promising in the context of natural language, since hierarchical structures in natural language are very natural and very important. So this is pretty cool. I think here we are slowly arriving to the conclusion, and I would, again, like to reiterate on some limitations of the study. Here we do not really claim that whatever constructions we have and we say, oh, well, SSMs should be able to express this formal languages, we do not really say that all of this should be also learnable or length generalizable. So in some sense, as we've seen in some graphs in the presentation, there is a certain gap either with the learnability or with the generalizability. So this work cannot really be used to claim any learnability results. And secondly, it would be better if we were able to expand the exploration of our positive claims with more empirical evidence. So in this work, we primarily use Mamba. We did include some results for Griffin. I don't think those results are included for every theorem that we have introduced. Just because we initially started working with Mamba and then we only included Griffin later, but testing out more SSMs would be cool from the standpoint of like, well, how about this gap between expressivity and learnability? And I guess another limitation is that some of our constructions are very tied to SSMs either being time invariant or non-negative, which might introduce specific caveats to how these constructions are done. So more careful study would be required on this exact implementation differences. And I'm also saying it because, for example, when we were talking about parity, let me maybe come back to that slide real quick. yeah, maybe here. When we were talking about parity, we were talking primarily about non-negative SSMs. So when we have the values of our matrix being non-negative, and that's primarily the bottleneck of why parity cannot be expressed. But since then, since our paper came out, that there has been work by a joint group of researchers from, I think, I'm not sure, not going to lie about it, but this was an iClear paper where they showed that if you do allow a matrix to take on negative values, then for sure, of course, parity is expressible and actually also learnable in practice. So certain design choices are definitely yet to be studied, and that's also one of the main limitations of this work, is that we don't really cover all of them. Otherwise, that would be too much. And I think in general, this would be it before I recap all the takeaways. So recapping our main theorems that we have introduced in this work. In finite precision terms, non-negative SSMs cannot recognize parity at arbitrary input length. They can predictively model a regular language if it's start-free. And the two-layer SSM can predictively model the flip-flop language at arbitrary lengths. This is guaranteed by Cronrode's theorem and Schutzenberger theorem, but not by our two-layer construction. Two-layer SSM can predictively model bounded Dike with the complexity of m log k. With a little bit of a modification to the finite precision, we can also say that SSMs can predictively model Dike 1, shuffle Dike, and so on. And yeah, that's actually it.
Thank you.
I think that's great.
Any questions? I think we can take questions in Russian.
We can try taking questions in Russian. I hope my terminology, we can take questions in Russian. I might be answering them in English, if that's fine.
Let's start. So, thank you for the brilliant and insightful talk. Я надеюсь, что дорогим коллегам, которые занимаются мамбой, удалось услышать, не знаю, много или немного, но что-то новое, что пригодится. Может быть, они сами выскажутся. У меня есть буквально пару вопросов. Один большой, один маленький. Большой вопрос такой. Насколько мне известно, мамбу все-таки, да, на практике тоже вполне используют, в том числе в виде комбинации в Mixture of Experts. И мне интересно, в общем, экспертное мнение. Есть ли смысл, да, вот попытаться рассмотреть, ну, вот с точки зрения теоретической, то есть с точки зрения принципиальной возможности моделировать разные классы языков, какой-то вот такой минимальный микстур, где есть и трансформер, и мамба. Имеет ли это смысл, или, может быть, уже какие-то результаты можно напрямую, так сказать, вывести из того, что есть?
Очень классный вопрос. Я, кстати, не знаю насчет Mixture of Experts, не слышала о применении SSMs там, и вообще, в принципе, честно говоря, не занимаюсь Mixture of Experts, но когда мы закончили вот эту работу, нам было очень интересно попробовать позаниматься экспрессивностью таких вот гибридных вариантов, но проблема в том, что там мы гораздо меньше можем сказать с точки зрения каких-то, допустим, можем сделать меньше предположений касательно finite precision, касательно, допустим, некоторые из этих конструкций, они очень зависят от количества слоев, которые мы используем. И в этом плане все эти конструкции, они очень теоретические, и они не всегда хорошо скейлятся на практике. Иногда это происходит из-за претренинга, допустим, потому что не очень понятно, что на самом деле происходит на фазе претренинга, непонятно, как архитектуры между собой взаимодействуют. Это было очень круто, это было бы очень круто, но я не уверена, что мы находимся в той точке, где теоретически это было возможно. Я знаю, что, допустим, с точки зрения взаимодействия агентов есть попытки, допустим, объяснить это с точки зрения communication theory и так далее, но мне неизвестно, как это может быть использовано пока что в таких вот более сложных сеттингах, как mixture of experts. Я думаю, что было бы очень классно, но практически создать такие конструкции будет очень сложно.
Ясно, спасибо. И второй вопрос, если можно. На 53-м слайде, да, вот говорили, что bounded dike, если на нем предобучить, то лучше, значит, решаются НЛПшные задачи. Все-таки, ну, то есть это понятно, что там какая-то посторонняя работа, но все-таки, какого рода задачи здесь рассматривались? Да, понятно, что НЛП задач много, то есть это буквально языковой
Language modeling, да.
Так, по одному. Спасибо. Ну да, makes sense.
Еще вопрос, коллеги?
У меня такой вопрос, я там, может быть, немножечко пропустил, когда говорилось про задачу parity, про отчетность. Вот там есть, на самом деле, же две разные вещи. Есть вычислять отчетность, а есть понять, что задача про отчетность. И вот именно стоял вопрос понять, что задача про отчетность, что дается много последовательностей, для каждой дается 0,1, зависит четное и нечетное, и потом это понимается. Потому что это я, ну вот насколько я это видел, вроде все архитектуры имеют проблемы с тем, чтобы понять, что задача про отчетность, ну вот в частности именно из-за того, что это очень шумный вопрос. То есть, потому что это, опять же, есть два разных задачи, когда система знает, что задача про отчетность, и мы хотим как-то, чтобы она ее вычисляла, или когда она на, там, не знаю, 1000 примеров пытается понять, что это задача про отчетность, ее вычислить. Вот что мы делаем? Второе, наверное, или...
Хороший вопрос. Я думаю, что в нашей трактовке здесь мы, скорее всего, ну, если мы говорим, наверное, в контексте recognition, то я бы сказала, что это больше про четное или нечетное конкретно. То есть
мы знаем задачу, то есть система знает, какую задачу решает.
Да.
Окей.
И при этом, как бы, predictive modeling нам просто позволяет в данном случае рассматривать эту задачу с точки зрения контекста больше похожего на language modeling. То есть в этом плане мы, наверное, больше ограничиваемся первым кейсом.
Понятно. Хорошо, да, спасибо.
Спасибо. Ну что, тогда, если больше вопросов...
У меня есть еще тоже вопрос. Большое спасибо, Яна, за интересный доклад. У меня такой вопрос, может быть, немножко в стороне. Вот когда-то, ну, мы все знаем эту историю, что вот когда, значит, у нас искусственные нейронные сети зарождались как идея, вот это понятие перцептрона, и была вот эта известная, значит, вот как бы история про то, значит, когда сказали, что ну, вот перцептрон, он там не может какие-то там функцию XOR как-то выучить, аппроксимировать и так далее, и поэтому, значит, вот вообще все это, значит, нас никуда не приведет. Вот я не специалист в той области, про которую вы говорите, но вот мне показалось, что вот этот доклад, он носит, ну, то есть вот результаты, они носят такой, в каком-то смысле, похожий характер, то есть мы берем, значит, некоторую там достаточно, ну, как бы достаточно такую как бы странную задачу, в каком-то смысле искусственную, чем-то похожую на вот этот XOR для перцептрона, и вот смотрите, какая-то, значит, мамба, какая-то нейросетевая модель, да еще и причем вот если в ее матрице только там, значит, положительные, отрицательные, неважно, но, в общем, какие-то ограниченные значения записаны, она вот эту, значит, специфическую задачку не решит, то есть вот этот язык специфически не смоделирует, ну, как бы и так далее. То есть это, конечно, само по себе, мне кажется, да, очень важно, правильно, здорово и хорошо, но не совсем понятно, а что из этого, так сказать, как бы следует, ну вот, на таком более высоком, что ли, концептуальном уровне. Да, вот, ну, по аналогии с перцептроном, ну да, там один он не может этот СОР аппроксимировать, а мы их соберем в слои, да, слои объединим в сеть, и все там у нас совершенно замечательно классифицируется, разделяется и так далее. Может быть, и вот здесь что-то такое тоже важно на самом деле.
Если я могу, правильно ли я поняла, что вопрос что-то из серии, а зачем вообще нам вот это вот, если мы можем вместо одного нейрона иметь там несколько десятков тысяч?
Ну да. То есть, например, как бы, то есть я понимаю, что это зачем, что это, ну, как бы ценно само по себе. Ну, у нас есть там результат, что non-negative SSMs cannot recognize parity, это окей, то есть это, в общем, perfectly fine. Я просто к тому, что, ну вот мы убираем non-negative, и сразу же вы сами говорите, что уже вот убрали, и все как бы становится хорошо. То есть какие мы можем выводы такие, ну, так сказать, более высокоуровневые, что везде на основе вот этих результатов, не знаю, с практической, ну, как бы точки зрения, я не знаю, с точки зрения моделирования, там, не знаю, не вот языка ноликов и единичек, и еще там с хитрой задачкой, а с точки зрения моделирования, не знаю, естественного, человеческого языка, там, английского, например.
Мне кажется, это очень классный вопрос. Я позволю себе тогда более длинно прорекламировать пейпер, который я здесь упомянула несколько вскользь. Сейчас, секунду, я, наверное, сделаю вот так, чтобы найти этот слайд. Да, вот нам на самом деле очень много подобных вопросов задавали, когда мы презентовали Expressivity в SSMs на Europe в прошлом году, и частично это мотивировало нашу вот следующую работу, которая сейчас на экране, я надеюсь, ее все еще видно. Born a transformer, always a transformer on the effect of pre-training on architectural abilities. То есть один из комментариев, который мы постоянно получали, презентуя эту работу, это, конечно, очень круто, что есть все эти конструкции, мы понимаем, что это важно, но не очень понятно, как это, во-первых, работает с настоящими языковыми моделями, во-вторых, как это скейлится, потому что, ну, мягко говоря, все люди, которые более, скажем так, работают с более эмпирической частью моделей, смотрели на нас несколько странно. Поэтому здесь, допустим, вот в этом пейпере, который сейчас на экране, мы показываем, что многие из этих архитектурных ограничений, то есть невозможность понимать, что такое parity, невозможность, допустим, когда у трансформеров они не могут, they cannot work with the flip-flop language, что это все также на самом деле в той или иной степени сохраняется, когда модели скейлятся до миллиардов параметров. Допустим, здесь мы смотрели на трансформеры, здесь мы смотрели не на SSM, но было бы, наверное, интересно посмотреть на SSM в том числе. Здесь мы вдохновлялись flip-flop language, и мы, допустим, пробовали это на более таких реалистичных тасках. То есть проблема у трансформеров была в том, что они не могут достать вот этот вот один бит после последней write инструкции, и мы смотрели, какие, допустим, естественные задачи похожи на вот это. И у нас есть в этом пейпере эксперимент, где мы давали моделькам там 7 миллиардов параметров моделька, лама, квен и так далее, до 32 би тоже скейлили. Это, допустим, если вы попросите модельку сделать, допустим, git revert или git cherry pick, то есть операции, которые похожи в своей сути более практически на вот этот вот flip-flop language, то трансформеры, допустим, подсунут вам не тот коммит, который вам нужен, потому что там нет семантических никаких подсказок для языковой модели. То есть там нет, допустим, части именно языковой, которая позволяет это легко делать в естественном языке, но при этом как бы есть настоящая реальная задача. То есть там покажи мне историю коммитов моих в обратном порядке. Сами коммиты, сами хэши ни о чем нам не говорят, но проблема в целом похожа на флип-флоп, и она сохраняется даже с большими моделями, то есть какие-то из этих вещей мы все равно можем перенести на реальный мир и на реальные модели. Я надеюсь, что это ответило на ваш вопрос.
Да, спасибо большое за ссылку, обратим внимание. Спасибо.
Хорошо, коллеги, тогда если вопросов больше нет, давайте еще раз поблагодарим.
Спасибо большое.
Вряд ли нас видят в этой библиотеке. Мы вам аплодируем.
Спасибо.
Спасибо.
Большое спасибо, что приняла приглашение на семинар.
Спасибо.
Интересно.
Всего доброго.
До свидания.